Welcome to Math 2318, Section 4.1. In this section, we begin to look at vector spaces. And what does that mean to be a vector space? Well, we have a set of objects. We have an operation called addition, that if we have two things in the set, the addition needs to be in there as well. And we have scalar multiplication. So in question 1 here, we have a collection of vectors. And this collection of vectors consists of all the vectors of the type x, y in R2, where the x coordinate is greater than 0 and the y coordinate is 0 or bigger. Alright, so it does not include points that live along the positive y-axis. Alright, so if I take two of these vectors in set V, question is, if I add them up, do I still get something in V? Okay, well, let's see. If U1 and V1 are both greater than 0 and I add them together, yes, the sum is still greater than 0. And if U2 and V2 are greater than or equal to 0, then the sum is as well. So yes, anytime I take two vectors in there and I add them together, I will get something else that's also of the same type. Alright, well, what about scalar multiplication? Well, let's see. If I take U, which looks like 2, 3, and I multiply this by minus 2 multiplied by that U. Remember, closed under scalar multiplication means I can pick any particular scalar that's a real number, positive, negative, 0. And so I would get minus 4 minus 6, but that's certainly not something that lives in that particular set. So it's not closed under scalar multiplication. And in the solutions, you have several options to pick. So you got to be careful here. For example, here in A, they have a U that looks like 2 minus 2. Well, that's not even in the original set, because the original set had to have something bigger than 0 and something greater than or equal to 0. So that's not even in the particular set. Alright, so their example falls into number D. Alright, in question 2, we have set W, and set W consists of things that live in quadrants 2 and quadrants 4. The product of the coordinates must be less than or equal to 0. Okay, so let's see. Here's a U and V. The product of the coordinates is less than or equal to 0. So they clearly are in W. What about if I add these two together? Well, if I add them together, I get minus 3 plus 0 is minus 3. 2 add a minus 5 would give me a minus 3, but the product is clearly not less than or equal to 0. Is it closed under scalar multiplication? Well, yes. In that case, if I multiplied C times a particular vector U, I would get a C in each component, and then irregardless of the C that I picked, I'd have C squared, and that part would always be positive, but the product would still be negative. So it is closed under scalar multiplication, but not closed under addition. Alright, in question 3. We have all vectors of the form x and y where 6x squared plus 6y squared less than or equal to 1. And so if you divide through by 6, you see that consists of all points in a circle of radius 1 over square root 6, centered here at the origin. And 1 over square root 6 is about 0.408. So, question is this a subspace of R2? Alright, so I picked a U and V, and which ones did I pick? Well, U goes all the way from the origin out to the edge. This one is 0, 1 over the square root 6, so that comes up to here. And when I add these two together, I get 1 over square root 6, 1 over square root 6. But is this new result still within this circle? And the answer is, let's see, square each component, add them up, I get 1/3. Is that less than or equal to 1/6? The answer is no. So it's not closed under addition of two items in the collection. If I picked, is it closed under scalar multiplication? Well, if I picked 1/4, 0, well, that does live within the circle. You can check that. But what about 4 times it? 4 times it, that scalar multiple, clearly does not live in there because 1 is not less than or equal to 1/6. All right. All right, what about if we have the set consisting of all polynomials of the form P of t is at cubed? Is it a subspace of P3? Well, what is this P3? P3 is the collection of all polynomials of third order form. So they can be of the form a3x cubed all the way down. So we're taking a particular subset, and that is just the ones of the form at cubed. For any a real number. Well, let's see, if I take two items in there, add them up, well, I can just add the coefficients once I factor out the t cubed. So, yep, that's certainly in there. Multiplying by a scalar, all right, well, I can just group together the c and the a, that's in there. The 0 is in there as well, so yes, this would be a subspace of P3. All right, we continue the same thing with Pn, the set of all polynomials of degree n. We'd like to find, we have the set H, which is all the polynomials in Pn, where we have the fact that P of 0 is 0. So let's say I take two of them in there where that's true. Well, if I add them up, I'm still going to get 0, so it is closed under addition. Let's see, what about if I have u of 0 is 0, and now I multiply that by a scalar. Well, that doesn't change anything. I still get 0. So it is closed under addition. It is closed under scalar multiplication. The 0 is in there because if I've got the 0 polynomial and I put in 0, I still get 0. So yes, it is a subspace. All right, we have H is the collection of all vectors of this particular form. and I want to show that it is a subspace of R3. R3, I've got three components here. So let's see, what do I do? I'm going to rewrite. So here's U, here's V. I'm going to check to see if I have them of these two forms. Can I add them up and get something of the same form? Well, yes, I simply factor out the 7 and the minus 6. 0 is in there, just let t be 0. Scalar multiples, yep, that's still in there as well. So you could physically check to see that if you do take something of that form, it will still be in there, so it is closed under the operations of addition and scalar multiplication. Another way of looking at it is you could form vector v, which is 7, 0, minus 6, and think of it as t times v. And so h is just the span, which consists of all linear combinations of v, and so that does form a subspace. All right, let's see in question 7. What if I've got vectors of this particular form? Is it a subspace of R4? Well, simply look for all the pieces that have an S in it. So that's nothing from the first part, a 5, a 4, and a 5. All the parts that have a T in it, a 3, a 4, a minus 4, and a 0. So what you can see is if you form the span of U and V, which is S times the first, T times the second, then you will get a subspace of R4, and it is spanned by these two vectors. What about matrices? All right, supposing we've got M 2 by 2, which is a set of all 2 by 2 vectors. I'm going to form a set H, which consists of all matrices of this particular form. A, B, 0, D. Well, is 0 in there? Well, yes, A, B, D could all be 0. If I take two vectors in there of that form and I add them up, do I still get something in there? Well, the answer is yes. Scalar multiples, yes, because c times 0 is still 0, and I still get something of that same form. So yes, that is a subspace.